All right, let's talk through how we draw Lewis structures. There are 8 steps to help you draw Lewis structures. First, find the total number of valence electrons in the compound. Then, identify the central atom. It's the least electronegative element in the compound, with the exception of hydrogen, because hydrogen can only have one bond. Connect all other atoms in the compound to the central atom by single bonds, counting each bond as a pair or 2 electrons. Add the electrons to the outer atoms to give each one 8, a full shell, remembering that there are some exceptions. Do the same for the central atom. Make sure that it has a full octet. Check, does each atom have a full outer shell? And then finally, have you used up all the valence electrons, or have you used too many? Let's work out a couple of examples now. Let's draw the Lewis structure for PCl3. The first step is to find the total number of valence electrons in the compound. So P has 5 valence electrons. Remember here, group 5A or 15. So here are its 5 valence electrons. And chlorine has 7. There are 3 of them. So to find the total valence electrons, we take 5 from phosphorus plus 7 from chlorine times 3 of them gives us a total of 26 valence electrons. Okay, then we identify the central atom and connect the other atoms to it by single bonds. So the chart here for the electronegativities is shown, demonstrating that phosphorus has a lower electronegativity and will then be the central atom. You can often generally, if you just have a 2-element compound like this, the one that comes first is lower in electronegativity, and or the one that has the fewest number of atoms will go in the center and the other atoms will connect to it. Okay, so we have phosphorus in the center. Connect each of the 3 chlorines by single bonds, so PCl3. So each one of these counts as 2 electrons, so 2, 4, 6 electrons are shown. Then we start with our outer atoms, and we add electrons to it to give each one 8. So this chlorine already has 2 electrons. So we have to add 6 more to get to 8. So 2, 4, 6. And I repeat that for each of the remaining chlorines. 2, 4, 6, 2, 4, 6. Now I do the same for the central atom. So right now, this phosphorus has 3 covalent bonds attached to it. That's a total of 6 electrons, right? Each of these dashes is 2 that are touching the phosphorus, so 2, 4, 6. So I need to put 2 more electrons on the phosphorus to give it 8. Okay. Now just check, does every atom have a full outer shell? Yes, every atom has 8 valence electrons. And then the final check and question is, have you used up all the valence electrons? Have you used too many or too few? So let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25, 26. So we've drawn 26 valence electrons on this Lewis structure. And remember, when we added up the total valence electrons at the beginning of this problem, we needed a valence electron dot or Lewis diagram that showed 26 valence electrons. So we've used them all, and this structure is complete for PCl3. All right, let's look at another example and draw the Lewis structure for NH3. The first step is to find the total number of valence electrons in the polyatomic ion or the molecule. So nitrogen N has 5 valence electrons, and each of the hydrogen atoms has 1 valence electron. So we have 1 for hydrogen times 3 total atoms, plus 5 valence electrons from nitrogen gives us a total of 8 valence electrons. Then we need to connect the atoms in NH3 by single bonds, by first determining the central atom. Generally, the central atom is the least electronegative, and that least electronegative element generally comes first. we exclude hydrogen from, even though it is less electronegative, because it can only form one bond. So what happens here is we put the N in the middle and we connect all the other atoms, the 3 H's, by single bonds. So we have a nitrogen connected to 3 hydrogen atoms. Each one of these single bonds is a pair or 2 electrons. So right now, each hydrogen has 2 electrons. 2 here, 2 here, and 2 here. And each nitrogen has 6, or this nitrogen, not each nitrogen, the central nitrogen has 6 because there are 3 bonds, so 2, 4, 6. We add electrons to the outer atoms to give each one a full shell. We have to remember our exceptions, right? Hydrogen doesn't need 8, it only needs 2. So each of these hydrogens is already stable with a full shell of 2 electrons. Then we do the same for the central atom. So we said that nitrogen had 6, 2 from each of these bonds. And we add 2 more electrons, 1 lone pair up here, to nitrogen to make 8. Now, every atom has a full outer shell, and we've used 2, 4, 6, 8 valence electrons, which was the total we counted at the beginning. So in this case, our valence structure for NH3 is done. All right, now let's practice and draw the Lewis structure for I2. Now, we have some element symbols. This is the element symbol for iodine. These are single bonds and lone pairs of electrons that you can drag and drop to form the compound. I'm going to just use my pen, but I'll show you how to drag and drop for this first example just so that you can see. So the first step is to find the total number of valence electrons. So iodine, is in group 17, so it has 7 valence electrons, each one, and there are 2 of them. So I need a diagram that shows a total of 14 valence electrons. There's no central atom here or anything. It's just 2 iodine atoms connected to one another. So I'm going to connect them by a single bond. Okay. Now at this point, I've drawn a single bond, so that's 2 electrons. That leaves me with 12 more electrons that I have to draw. So then remember the next step is to complete the octets on the outer atoms. Again, there's no outer atom here. We just have 2 atoms bonded. So I'm going to just start with 1 iodine. And iodine is stable when it has 8 electrons. So right now, this iodine only has 2 from the single bond. So 3, 4, 5, 6, 7, 8. So that's, I've drawn 6 dots, right? Then I need to do the same to the other side. So 6, 1, 2, 3, 4, 5, 6. So those little black dots, those lone pairs of electrons, they add to 12. If I subtract 12, I've now used up all of my valence electrons. I can't draw any more, but I just need to do a check and make sure, do each of these iodine atoms have 8 valence electrons, and are they both stable? And the answer is yes, they are. Now, if you were doing this in the classroom, you wanted to call up a student, or you wanted to show the dragging and dropping, you could just drag the 2 iodines, connect by a single bond, and then I'm not going to drag 12 of these, but you can see that you can just drag electrons around, and you would do 2, 4, 6 for each one, okay? Until you got to this structure for I2. All right, well, let's do the same thing with this next example. The font here makes this a little bit confusing, but this is Cl2, so 2 chlorine atoms. It looks exactly the same as the one we just did. Chlorine is in group 17, so it has 7 valence electrons. There are 2 of them, so a total of 14 valence electrons. We connect each of the chlorine atoms by a single bond. So we've used up 2. Now, each chlorine right now is sharing a pair of electrons. They each have 2, but to be stable, chlorine needs 8. So I need to add some valence electrons to each one. So 2, 4, 6. So now this chlorine has 2, 4, 6, and then these 2 make 8. And I do the same thing over here, 2, 4, 6, and then this pair that's shared makes 8. So I've drawn a total of 14 electrons, 1 bond, and then 6 lone pairs, or 12 electrons. So I've used all 14 electrons. Each chlorine atom is stable, and this is a complete Lewis structure for Cl2. And let's practice another one, CH4. So first we find the total number of valence electrons. Carbon in group 14, or 4A, has 4 valence electrons. Hydrogen has 1 valence electron, and there are 4 of them. So that's a total of 8 valence electrons. Then we start with the central atom in the middle, generally the least electronegative atom. In this case, remember, hydrogen always goes on the outside. So carbon connected to 4 hydrogen atoms. Now, I've drawn 4 bonds. Remember, each of these dashes is 2 electrons, so that's 8. 2, 4, 6, 8. So I've now used up all of my valence electrons, but I need to make sure that all of these atoms are stable. So remember that hydrogen is one of those exceptions. It's stable with only 2 valence electrons. So each of these hydrogens has 2 because each of them has a single bond. So here's 2, here's 2, 2, 2. So our hydrogens are okay. And our carbon in the middle, each of these is 2. So it has 2, 4, 6, 8. So everything is stable here. There's no electrons left over, so we don't have any lone pairs. We just have 4 single bonds. And here's our final structure for CH4.